Hello, I'm Doug Cotton, and it's always troubled me that climate change perhaps isn't man-made. I first learnt physics and did a degree in it some 50 years back, and I've helped many students over the years understand physics, and that's what it's all about, and I hope I can help you too. What I'm bringing to you though is not 19th century or 20th century physics, but it's something that's 21st century physics, a new paradigm when it comes to atmospheric physics. It's something that has only been proven empirically in this 21st century, just these last few years. So it's new stuff. And I've spent thousands of hours bringing together the work done by various scientists to fill in the jigsaw puzzle of climate change. I want you to put aside all ideas of greenhouse effects. Let's just go right back to square one and try to discover what actually happens, not only here on Earth, but on other planets that have atmospheres, like Venus and Jupiter and Saturn and Uranus and Neptune. Why is it that the surface temperature on these planets is what we observe? Here on Earth it's quite a nice, pleasant, comfortable temperature to live in, but up on Venus it's something like well over 400 degrees centigrade. And people say, oh, Venus has got an atmosphere that's made of carbon dioxide, it must be a runaway greenhouse effect. And they say therefore one molecule in 2,500 air molecules here in this Earth must be having a greenhouse effect. And what is this greenhouse effect? Well, basically they say it's due to radiation sending energy back to the surface from the atmosphere and slowing down the rate of cooling. And you know, that's quite true. That's what physics says. It does happen. Radiation from a cooler source can slow down the rate at which a warmer source, a warmer target, the Earth's surface, cools by radiation. But note those words, by radiation. In my first paper published in March, what I'll tell you about later, I showed that radiation can only affect that component of surface cooling which is by radiation itself. Now, of all the energy that comes from the sun into the surface and then comes back into the atmosphere, less than 30% of that energy actually transfers by radiation, and it's scattered way up through all the various altitudes in the atmosphere. It doesn't necessarily affect very much of the air we breathe, where we measure temperatures in the first couple of metres or so above the surface. There are other processes going on that help cool the surface. These are non-radiative processes, and the most important of these is perhaps evaporation, and also something that you probably don't really know very much about. This can be loosely called conduction, but strictly between a solid and a gas it should be called diffusion. And this process of diffusion continues in the atmosphere itself, among the very little molecules in a gas. Let me explain. When these molecules collide with each other, they transfer energy, just like billiard balls when they hit each other. This is kinetic energy that is transferred from one to the other, and it is shared. So you know that if you have a heater in one corner of a room, gradually that warmth will spread throughout the room, even when you turn the heater off. If you just run it for a short time, for example, in one corner, turn it off and wait for a long enough time, you'll find a more even sort of distribution of temperature throughout the room. But way back in the late 19th century, a scientist by the name of Loschmidt postulated that perhaps the temperature is just a tiny bit cooler at the top and a little bit warmer at the bottom. But in those days there were no instruments that could measure very fine differences in temperature, like 1/100th of a degree. And that's about all we might have expected. Why is this so? Why could this happen? How could this happen? Well, we need to understand what temperature is. Temperature is a measure of the average or mean kinetic energy in a molecule. That's the energy associated with movement and vibration and rotation. And this energy is what is measured by a thermometer or any temperature measuring device. But molecules have other energy. They have what we call potential energy, which is similar to what Newton discovered when he saw an apple fall from a tree. The apple had more potential energy on the tree, and it lost potential energy as it fell. And as it fell, that potential energy converted into kinetic energy. And that's exactly what happens when molecules move between collisions. There is a change, there is a transfer of potential energy to kinetic energy, or kinetic energy to potential energy, if they are moving upwards. And of course they're always moving a little bit upwards or a little bit downwards. And so what happens is that in any particular region we find that in fact those molecules that happen to have ended up down lower end up with more kinetic energy. Suppose they all started in the middle layer of a room, and some moved up and some moved down. Perhaps you can understand it that way. You can understand it perhaps more if you read in detail a new paper that I've just had published. I'll get to that later. But this concept of diffusion is what is critical, absolutely critical in an understanding of atmospheric physics. And the other thing that's critical is to understand that when, for example, you shine an electric radiator on some object, it only heats up to a certain temperature and it stops at a certain point, not because it's as hot as the radiator, but because it's reached a point where its own radiation, sending the heat out again, balances the amount of heat that comes in. And that's exactly what happens with the whole of the Earth system, including its atmosphere, and the whole of Venus, including its atmosphere. That complete system radiates back the same amount of radiation that it receives from the sun. But the important thing about diffusion in the atmosphere is that it sets a thermal gradient. It makes sure that the atmosphere has to be warmer at the base than it is at the top of the troposphere. And that's the main part of the atmosphere we need to talk about. So we find that for roughly every kilometre that you rise in the atmosphere, the temperature drops by roughly 7 degrees or so. And this can be shown, this can be calculated, and it's found to be a function not of carbon dioxide concentrations or anything like that, but a function of the acceleration due to gravity. That actually then has to be divided by what we call the specific heat of the actual atmosphere. And this gives us close enough to the gradient that we expect. There's a slight reduction because there's some radiation going on in the atmosphere that can send some heat to cooler parts of the atmosphere and just make that gradient a little bit less than what we calculate. But that's the concept. Now, that gradient has to be there in any atmosphere. It doesn't matter whether the surface plays a part in this or not. It has to be there. And we can see this on the planet Venus because we find that the surface of Venus receives less than 10% of the amount of energy that Earth's surface receives directly from the sun. The vast majority of the energy reaching the whole system at Venus is going into the atmosphere and warming that over the course of millions of years. It's reached the temperatures that it has, but it's still cool at the top and it's very, very hot at the base. And it would have been like that quite regardless of the surface temperature. The atmosphere got to that temperature first, so to speak. It's not the surface heating the atmosphere on Venus. It has been the atmosphere heating the surface. And that's the paradigm shift that we have to focus on. Now you can read about this in my papers. Where are these papers? Well, they've been published by an organisation called Principia Scientific International. You can just Google that and find their website. And you can look in both the PROM menu, which stands for peer review in open media, and you can look in the main publications menu, and there you'll find my papers, one of them on radiated energy, the other on planetary surface temperatures. So look it up, Principia Scientific International. You'll find their website quite easily, and there you can read in more detail about this 21st century physics, which completely overturns the concept of any greenhouse effect.